All right, I'd like to talk about Euler's formula, famous identity concerning the exponential function, relating e to the x to sine and cosine of x. How could these functions be connected? Well, we're going to see. So first of all, I want to be careful how I define the exponential function. There's more than one way of defining it. We could define it, say, in terms of a limit. I believe it's something like limit as k goes to infinity of 1 plus x over k to the k, something like that. Or we could define it via its differential equation, whose derivative is equal to itself with the initial value f of 0 is equal to 1. There's all kinds of ways to define the exponential function because it has so many wonderful properties, but I want to hone in on the series definition. E to the x, we'll just use this to mean define, to be n is equal to 0 to infinity, this infinite sum of x to the n over n factorial. Or term by term, this is going to look like 1 plus x squared over 2 factorial, which is just 2, plus x cubed over 3 factorial, which is 6, plus, and so on, all the way up to infinity. And normally, when we're looking to see if a series converges, which we know this one does, one thing we might do is we might say, does it absolutely converge? For instance, given some particular x, does this series converge, which ends up being equal to absolute value of x to the n over n factorial. And it does for all x, which is why e to the x is defined for all x, or one way of thinking about that. So, with this idea of absolute convergence, the stronger form, the kind we really want in an ideal situation, what happens if we replace this real number x with a complex number z? Well, we know that in the complex plane, you can think of a number as sort of a vector pointing to x plus iy, right? So you know that it's going to have some length, and it's also going to make some angle theta with this x-axis, this real axis. But what's going to happen when you multiply by a complex number? Well, it's either going to get longer or it's going to get shorter, and then it's going to rotate by some amount, right? That's all that can happen to this number. But we don't really care about the angle, just as in the case of a real series, if we had like a -1 to the n in there, that's not going to force it to diverge. In fact, if it converges without that, then we know it converges with that, because it's just going to bounce back and forth closer and closer to 0. Same thing is going to happen in the complex plane. We don't actually care about this angle so much. We care about this distance from 0. And what is that? That's the modulus of a complex number. So the modulus, or rather the modulus squared, let's define that, is equal to a complex number times its complex conjugate, right? So that if z is equal to x plus iy, then z bar, or the complex conjugate of z, is equal to x minus iy, where we've essentially made a transformation from I to negative I. And this is what we get. When you multiply them together, you get x plus iy times x minus iy is equal to x squared plus ixy minus ixy, so those terms cancel. And then here you have an I times a negative I, which is going to just be positive 1, and then y squared. So x squared plus y squared. And so you notice that this is just the distance from the origin in the normal plane, right? So that the modulus is going to be equal to the positive square root of that number, where x and y are both real numbers. All right, so what we really are interested in showing is that we have absolute convergence, at least in an ideal situation. So what we can do is, instead of taking the absolute value of this, let's take the modulus, the complex modulus of this I almost said integrand, summoned don't use that word every day, and see if it converges. And what's this going to be? This is just going to be the sum from n equals 0 to infinity of modulus z to the n over n factorial. And modulus z is just going to be a real number, and we happen to know from what we know about the exponential function already that this converges for any real number mod z. So that means that it is going to absolutely converge in the complex plane, so the e to the z is always defined for complex number z. So it is safe for us to define the exponential function in this way. Alright, now that we know that it converges and that this function is well defined, let's do a special case. So what if we were to plug in z equals ix, where x is a real number, so we're going to plug in a pure imaginary argument. What would we get? Well, by this series definition, e to the ix, which we now know is defined, is going to be equal to the sum from n equals 0 to infinity of ix to the n all over n factorial. Now, let's write this out term by term so that you can see a pattern that we're going to find. This is going to be equal to 1 plus ix squared over 2 factorial plus ix cubed all over 3 factorial plus ix to the 4th power over 4 factorial, and so on. Let's actually multiply out, square these x's and i's, and cube and so on. 1 plus ix plus I squared is negative 1, so this is actually going to turn into minus x squared over 2 factorial. Similarly here, we're going to get I squared equals negative 1, so that I cubed is negative I. So this is going to be minus ix cubed all over 3 factorial. We're going to get I squared times I squared, which is going to be positive 1, so plus x to the 4th over 4 factorial, and so on. Now, because it converges absolutely, we're allowed to play around a little bit more with the terms, right? That's how series works. So we can actually factor this and pull out all the terms that have exactly one I in it. Because if you're clever, you'll notice that for every other term, there's going to be no i's in it, because an even I to an even power is going to give you a real number. But to an odd power, you're still going to have a factor of I left over. So let's split those up into 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. And then factor out the number I. And what do we have? We have x minus x cubed over 3 factorial. Should make sense to you that the next term is going to be plus x to the 5th over 5 factorial minus etc. etc. Now, you may or may not recognize these, but these, if you've studied series at all, these are familiar to us. So let me just write it in summation form, just for completeness here. It's going to be equal to the sum from n equals 0 to infinity of x to the 2n times negative 1 to the n to the n, yes, all over 2n factorial. You see that? We're getting the even powers and the even numbers in the denominator. And this is going to be plus I times the sum from n equals also 0 to infinity of x to the 2n plus 1 times negative 1 to the n all over 2n plus 1 factorial, where we're getting only the odd powers of x and the odd numbers in the factorial here. So, we should recognize both of these infinite series as a Taylor series for functions we know and love. This is none other than cosine of x plus I times the sine of x. So if we write down here e to the ix, we get e to an imaginary argument is equal to cosine plus I times the sine of that argument. This is known as Euler's formula and is very cool and very useful. As one illustration of how cool it is, we will plug in x is equal to pi. This will give us e to the I pi is equal to cosine of pi plus I times the sine of pi. What is this equal to? Well, the sine of pi is just going to be 0, and the cosine of pi, 1, 0, negative 1, 0, is going to be negative 1. So e to the I pi, if we bring that 1 over, plus 1 is equal to 0. This is called Euler's identity and is very famous because it connects the number 0, the number 1, the number I, the number e, and the number pi. These really fundamental constants in math, or at least seen as so, all in one cute little identity. Isn't that remarkable? In addition to that, we can think of e to the I theta equals cosine of theta plus I sine theta. We can think of this as its own complex number, right? X plus IY. And so that means we could plot this in the complex plane. Let's see what happens when we do that. Well, this is the complex plane. Well, so what we're going to have is all the points whose x-coordinate is equal to cosine theta, and whose y-coordinate, if you will, is going to be equal to sine theta. That's going to multiply, right? That's the imaginary component. Well, wait, this looks familiar. What happens if we take x squared plus y squared? Just humor me. Is equal to cosine squared theta plus sine squared theta is equal to 1. Thus, this is the magnitude, by the way, of this number. E to the I theta magnitude is equal to 1, which means it is none other than the set of points which are exactly distance 1 from the origin in the complex plane, or the unit circle. How do you like that? Another way you can think about this is that we are taking the number 1. We're starting there on the real axis here, real, imaginary. And what we're going to be doing is we're going to be rotating by this angle theta. And what's that going to give us? It's going to give us exactly this point on the unit circle in the complex plane, which is separated from this by angle theta. That's equal to e to the I theta. And in fact, because rotations have this wonderful property that you can follow them up, so that e to the I theta, and then rotate after that times e to the I phi is equal to, again, a wonderful property of the exponential function, e to the I theta plus phi. You can talk about this operation of rotation and it becomes a group, right? And I've talked about groups before, and you can look elsewhere for information of that. But specifically, when we talk about the unit circle and the complex plane parameterized in this way, what we're talking about is a famous group called the special unitary group of 1, SU of 1. All this just from plugging an imaginary number into the exponential function and using this wonderful formula, Euler's formula, to do all kinds of stuff. And this is only the beginning.